My topic today is the McCabe-Thiele system for analyzing steady-state distillation columns. So binary distillation is the topic today, and this is a very classic subject in chemical engineering. There is a lot in the literature about this method, and I wanted to just walk through so that we would understand what we were doing when we could do this calculation for the number of trays in a distillation column. So here is my schematic of binary distillation, and the McCabe-Thiele method uses the assumption of constant molar overflow, which indicates that the liquid and gas flow rates in the upper section or the enriching section of the distillation column will be represented by a single liquid flow rate and a single vapor flow rate that's independent of which tray you're in, as long as you're above the feed. And also that below the feed, there is a single liquid flow rate and a single vapor flow rate that is characteristic of any equilibrium stage below the feed. And that greatly simplifies the mathematical analysis of a steady state distillation column. It's of course not always true. Here's a list of the requirements for the chemical system, binary system of A and B, that the system would have to meet for this to be true. And I send you to the literature to understand better where those constraints come from. The reference that I used here is separation process engineering. All right, so I want to have a guidepost to take us through this calculation. Our goal is to determine the number of equilibrium stages that are needed in a distillation column to make the actual separation take place that we assert. So that is our goal. And these will be the different constraints from the physical world, from the real world, that we have to match in order to have that be the case. So we have to have masses conserved. Since we have no reaction, those will be mole balances. We're going to assume that all the stages are equilibrium stages. And so equilibrium stages mean that we can go to the literature and get the physical property data for the material that we're dealing with and find out what kind of liquid vapor equilibrium that material actually exhibits. And so, for instance, I'm going to draw the equilibrium stages like this and say we have a liquid and we have a vapor. And in the liquid phase, we have species A in mole fraction XA, and 1 minus XA is the mole fraction B. And in the vapor phase, also mole fraction, I'm going to call that Y. YA is the mole fraction of A, and 1 minus YA is the mole fraction of B. When I'm actually talking about two phases in equilibrium, these are sometimes designated with a star, that they represent the saturated case. And this equilibrium curve is data from the literature of Y star versus X star that indicates that there is an equilibrium. So this is Y star as a function of X star. We're going to use Y and X in this plot for a bunch of other things as well. And so that'll be part of what I want to convey as we speak. So this is quite crowded, and we've got a lot to deal with in these calculations. So we're actually just going to write XA here and YA here. And we just have to remember that we're talking about a binary mixture. Actually, even that's a little bit complicated. We're actually going to just call it X and Y for the particular stage we're on. So if this is stage 9, this would be X9 and Y9. Those are the two compositions that are in equilibrium with each other. So we're simplifying the nomenclature a little bit just to keep us on top of the calculations that we're doing. So equilibrium stages. All stages above the feed satisfy the same mole balances written through the upper distillate stream. So that means that if I draw some kind of envelope here to indicate where I'm doing my mole balance. Above the feed, as long as I'm above the feed, they all, no matter which stage I pick above the feed, they all have the same mole balance. And then below the feed, where they have the L bar and the V bar, we can do a single balance below the feed. So that is a reflection of this constant molar overflow assumption that's part of the McCabe-Thiele diagram that says in the enriching section, the upper section, there'll be this single value of the liquid flow rate and a single value of the vapor flow rate. And in the stripping section below the feed, there'll be a single value of the flow rate and a single value of the vapor. So these, we'll be applying those mathematically. And then those two balances have to meet somewhere. They meet at the feed stage. So at the feed stage, we have a special stage, and we have to make the mass balances above and below match at that point. And then there's the quality of the feed. So the final piece of physics that cinches this calculation is to know if for the saturated mixture of saturated liquid and vapor that comes in the feed, how much of it is liquid and how much of it is vapor. So these are going to be the constraints that we use, and I'll point out when we do each one. So let's start with the overall mass conservation. So let's start with this binary distillation column. And the overall mass conservation would be us picking the overall balance. So it's a classic first course in chemical engineering calculation. So we have the flow in equals the flow out at steady state. So F is equal to D plus B. This is the total moles balancing. But we also will balance the moles of A. So the moles of A in is XFF in, and XD flow D out, XB moles B out, and we've written down the constraints for the overall mass conservation. So the next constraint is that we have equilibrium stages. And so the equilibrium stages means that when I draw, as I did a moment ago, a particular stage, the liquid and the gas liquid and the vapor are going to be at equilibrium in that stage. And therefore I should be able to relate, if I'm given the X value, I should be able to get the Y, or if I'm given the Y value at the equilibrium stage, I should be able to get the X. So we've got the Y star as a function of X star constraint. So now we go to the third one. All stages above the feed must satisfy the mole balances. So here's our total distillation column, but I'm going to do a balance just above the feed. So that would look like this, drawing it separately. So now we have, we've cut through the column. And so there are, in fact, liquid coming down and vapor coming up, right? And so I'm just going to pick an arbitrary number for this stage. I'm going to say that this is stage 2. It could be any number. I could put a J. A lot of books will say, oh, stage J, but that's maybe a little confusing. I'm going to pick a number, stage 2. Okay, so I'm going to do a balance at stage 2. So this stage has stage 2. It has liquid here, and this liquid has composition X2, and it has vapor composition Y2, but that's not where I'm drawing my balance. I'm doing my balance all the way around the outside. But this stream is the stream with molar flow rate V, vapor coming up from below, and it comes from the next stage. So that's stage 3. So this is Y3. So as if there were another stage outside of the view, and its material comes up here as Y3. So up here at the top, it's not quite finished how it's drawn either. We're going to consider the usual case of a total condenser. So a total condenser means that this stream, which came out of tray 1, which means that it's Y1, every tray is an equilibrium tray, and the compositions of the equilibrium phases are named for the tray number. So it comes up as Y1, it goes through the total condenser and comes out as XD. Well, that just must mean that Y1 equals XD, right? Because if I totally condense the stream, it has the same composition when it was a vapor phase as it does when it's condensed. And I know what that value is. So Y1 equals XD. And then usually we reflux. So we have to reflux a stream here. And we're going to reflux by the amount L, which is the downwardly flowing L that goes through the column. I'm drawing those details so that we can pull out this Y1 equal X2, but the actual balance I want to do is on the outside here. It's good for any of the tray numbers that are above the feed. Okay, so that's the balance I'm doing. And so it's always, in a complex problem, it's always nice to draw the envelope so that we can get it right. So we can draw the total of moles balance. So there's V, and there's not, that's the only one there is, and out there's L and D. Then we can do moles of A. And so in is Y3V plus nothing equals X2L plus XDD. Okay, so that's the balance. So we can work on that a little bit. We'll take that first one. And divide through by V. Okay, so we have Y3 equals L over V times X2 plus D over V times XD. D over V, let's see, we can go back up to this expression to get rid of the D. Okay. So I'm going to put in that D equals V minus L from the total mole balance up here at the top. Okay, D is equal to V minus L. And so I get L over V X2 plus V minus L over V XD for equals Y3. So this is the balance across the upper part of the column. And these two streams here at the bottom, these two streams are called passing streams. So these two streams pass by each other. So whether I drew this red loop anywhere in the upper section, there would always be two passing streams. And they would always be labeled with the liquid phase composition being one less than the vapor composition. So it would always be Y3, X2, Y4, X3, Y5, X4. So those are the passing streams. So I can write the balance I just did for these passing streams as generally true for Y and X in this upper section, in the enriching section of the column. So Y L over V X plus, well, I can say 1 minus L over V XD. So this is a line, Y versus X. It's a line that represents, that we can draw here on the XY graph just because we want to. And we could draw some kind of a line. And it would tell us as a function of X, how the X and Y have to be related to each other in order for the enriching section mass balance to be satisfied. This line is called the operating line. for the enriching section. Now let's notice that this passes through the point y equals xd. I mean, y1 equals xd. So let's try that. So we talked about the fact that here at the top with the total condenser, that because we totally condensed this stream, which was a vapor, into this liquid stream, which we labeled as having a liquid phase composition of xd, but they're actually equal to each other because of this total condenser situation. So let's just, let's say, plug in that point. So there's our operating line. And so let x equal xd. Let's just, it's a function. We can plug that in, and we get that the y that goes with it, that's a passing stream in the enriching section, is L over V xd plus 1 minus L over V xd. And so we've got L over V xd plus xd minus L over V xd. And so these cancel, and we get y equals xd. So the point y equals xt is on the line. And that would be whatever stage we pick. Okay, any stage we pick. This is the operating line for the upper section and the enriching section. And we found that y equals xt is on that line. So that inspires us to go over here to our graph. And I'm going to switch to some smaller pens just because it's going to get crowded. And I'm just going to say, well, I'm just going to say that xd is this number, which is 90 something or other. I'm just using an example bit to show you how we use the graphical method. Okay, so if this is xd, then y equal xd means that on this 45-degree line that's sketched in, I would expect, this is one of the points, y equal xd, that's on the operating line. So this point is on the operating line. And the operating line is a straight line, y equals slope. Okay, so this is the slope. Y equals slope x plus intercept. And so L over V is the slope. And so I don't know what the slope is right now, but there's some line that has a slope that gives y as a function of x for the upper region of the column. So that constraint here is satisfied. All stages above the feed satisfy the same mole balances drawn through the upper half. So then we now go to the next step, which is to talk about the bottom of the column. So the whole column looks like this, and we can draw a loop to indicate where we're going to do the balance on the stripping part of the column. And as long as we're below the feed, that will be the stripping section. And it'll have to go through this point B, this stream B that's here at the bottom. And so here we have it. So this is below the feed, so the feed stream doesn't show up. Again, the liquid streams have to come down and the vapor streams have to go up. But as we said here with the constant molal overflow assumption, these will be given by the barred flow rates that are not the same as the unbarred flow rates. Okay, so the liquid stream cutting through any tray that's below the feed comes down as L bar V bar. And then there'll be some kind of whatever tray we're on. And so I just need to use some kind of an example. And so I think I'm going to pick that this is this came down from tray 5, and this is coming up from, so this tray here will be tray 6. So da 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 da. So this Y6 is in equilibrium with this X6, but this liquid stream comes from the one above. So this has composition X5. So now we're just going to carry out that balance that, that we want to do. So we'll just draw ourselves a little envelope. Don't have to worry about that total condenser business because we just have this stream at the bottom, and then we do the balance. So we can do the total balance, or the, yeah, total moles. And so in is L bar, and out is V bar and B. And we can do the moles A balance. So in is X5 L bar, and out is Y6 V bar plus XBB. So we're going to follow the same ideas that we did the last time. We'll just simplify this equation a little bit so we can get the operating line for the bottom half of the column. So I'm looking to have y as a function of x. So I'll say y6 v bar equals x5 l bar minus xb b. And now I'll divide by v bar. Y6 equals L bar over V bar, similarly to before, only now it's the barred ones, minus B over V. And from the balance above here, B is equal to L bar minus V bar, right here, L bar minus V bar. And so we get Y6 equals L bar over V bar, X5 minus L bar minus V bar over V bar times XB. I missed the XB here, XB. So as we did previously for the upper section, we'll recognize that this could have been done for any stage below the feed. And these are two passing streams. Okay, these are also two passing streams. And so we can just call them Y and X passing streams below, below the mean. And just to remind us that, I'll call this one Y bar. And this one X bar. And we end up with, again, a general equation, which is the operating line for the stripping section. So this balance is true for all possible balances I might do through any equilibrium stage that's below the feed. And so we don't know what this slope is, just like we didn't know what the slope was for the upper section, but we're heading towards that. But we do know one point. Again, we can ask about the bottoms. Okay, so let's see what happens, just like we did last time. Let's try, let x equal xb, and let's plug it into the operating line. Okay, so y equals L over V xb minus L bar over V bar minus 1 xb equals L bar over V bar xb minus L bar over V bar xb plus xb. So these two cancel. And we get that Y bar equals xb. So again, we've identified a point on our XY graph. I have to dig it out of my papers here. Somewhere I have, there it is. Y bar equals XB. So this is again a point on the 45-degree line. So there's a Y that's a function of X. There's some sort of a line down here in the stripping section that has some kind of a slope, but we do know one of the points, and that point is the point that's at XB. So I'm going to use, again, just for illustration, a value of XB that's somewhere below 10%. So I can say, well, let's let this be XB. So if that's XB, then this must be the Y that goes with it. So this is XB, and this is the Y of the last tray, okay, the absolute last tray. So I'll just put that dot on there. That's in the operating line for the stripping section. So the stripping section has some sort of a line that has to go through that point. And the enriching section has a line that has to go through this distillate point, okay? And then we have this other curve which represents all the equilibrium stages in between. So we've now done the balances on the stages below the feed. So the next step is that all the upper and lower lines intersect. Those two lines must intersect at the feed. Okay, so let's start by drawing the feed tray just to keep track of what we're doing. And I forgot that I have a little feed tray here. All right, so the feed tray is a very special tray that has, again, liquid coming down, vapor going up from the upper section. So those are the unbarred flow rates. And then liquid going down and vapor going up in the barred section, in the stripping section. So that's at the feed tray. Okay, at the feed tray, there are different vapor and liquid phases because there's a feed stream coming in that has to be taken into account in doing the actual balance. So I'm going to call, so this is again, this is some kind of equilibrium stage. I'm going to call this stage 4. Let's say the stage is 4. Again, I'm using specific numbers just temporarily so that you don't have to put up with arbitrary J's and F's and things like that. But you know, it's going to be some stage. I don't know what stage it is, but I'll take the 4 out maybe almost immediately. So this would be this is an equilibrium stage. So this would be X4 and this would be Y4, and they're in equilibrium with one another, and so they would be on the equilibrium curve. I'm going to call this X tilde, the general feed tray, and this is Y star of X tilde. Okay, that's how I'm expressing that the two compositions in the feed tray are also in equilibrium stage. Okay, so notice, okay, this X is liquid coming down here. So this is X tilde or X4. And this is the vapor leaving the feed tray. So this must be Y4, which is the same as this equilibrium phase. So I don't want to clutter my diagram or I'll get confused. So I'll just call it Y4 here for a second. Okay. And now if this is Y4, then this stream must have come down from one stream above. So this must be X3 coming down from the stream above. And if this is X4, this must be going up from the stream, from the stage below. So this must be Y5. So you see, I could have done n+1, n-1, all that stuff. But let's just use numbers so that we don't get confused. All right, so we want to apply the constraint that the upper and lower operating lines intersect at the feed tray. So I have the upper and lower operating lines. Here's the lower one with the bars. And in my pile here, here's the upper one without the bars. And so I should be able to plug in the passing streams for this. And so the passing streams are X tilde here, and I'm going to call this one the other passing stream, Y tilde. Okay, so X tilde and Y tilde are passing streams. So that, what's important about that is we have an expression for the passing streams in the enriching section. So I could just plug in X tilde, Y tilde there. And then we also have the operating line for the stripping section. So I can just plug in the X tilde, Y tilde there. And then I'll have two equations. All right, so let's do that. At the feed stage, we have, I'm starting with the enriching section. I'm just going to copy the enriching equation with the Y tilde in there. So Y tilde equals L over V X tilde plus 1 minus L over V XD. And then I have the stripping section. Okay, Y tilde also has to be satisfied at the feed plate. Y tilde equals L bar over V bar X tilde minus L bar over V bar minus 1 XB. So I'm going to combine these two streams together and get an expression for a constraint that has to be held at the feed tray. So I'm going to subtract. So first, let me, before I subtract, I want to put these into a slightly different form. I'm going to multiply that V through. So it's Y tilde V equals L X tilde plus V minus L XD. Well, actually, I'm actually just going to go back to the operating line expression, and rather than reverse all this algebra, I'm going to use this version of the operating line. Okay, this version right here. So I'm just going to stop myself for a second here and redo this page 8 and say at the feed, I'm going to use, so this is the operating line for the stripping section before a little bit of algebra, this version. So this is going to be Y at the feed, V bar equals X at the feed, L bar minus XB. So that's for the bottoms. And then if I go back in through my algebra, you'll just hang on for a second. Hopefully I can find it. Well, I haven't found it. So this is in the stripping section. And a few steps above this, maybe I can find it here. Here we go. No, can't find it. Yeah. So a few steps above this. No, that's not the right one. There's the version for the enriching section, which when you plug it in for the feed station is Y V bar equals, excuse me, not V bar, YV for the stripping section equals X tilde L plus XDB. So these are the versions of the equations that have the distillate phase in it and the bottom phase in it. And I apologize for not being able to find them in my notes, but they're just before the derivations of the operating lines that I did. And this is the version that's going to lead to the McCabe-Thiele. I'm going to subtract them. So there's no magic, even though I kind of had a little skip up there with the algebra, but these are just the mass balances for the upper section and the lower section. So now back to the subtraction. So we get y tilde equals, we're going to subtract the bottom from the top. So this one, well, I shouldn't say bottom because I have that means something in this. I'm going to subtract 2 from 1. All right. So y tilde times v minus v bar equals x tilde times L minus L bar plus xdb plus xbb. So, okay, so this is a typo. This is a D. The D's have to match. And therefore this one is a D as well. From the overall mass balance, we know that these two streams must equal XFF. So these are the two streams that come out of the distillation column. And so we get the final expression for passing streams at the feed tray, which is y tilde equals, I'll divide through by this one, L minus L bar over V minus V bar, X tilde plus XFF divided by V minus V bar. The upper and lower operating lines intersect at the feed tray, which means at the feed tray, the conditions, the X and the Y that show up in the feed tray have to follow this expression for what the passing streams have to be related between the two. So we've now used that, applied that constraint. And we have just one more, so we're almost done. This is also a line. Okay, so this is a line of Y versus X that expresses passing streams on the feed tray. And so at the feed point, which I'm going to put at, approximately halfway here, just for fun. Again, I'm just making these numbers up for illustration. So here at the feed, so this is going to be X feed, there's going to be some relationship that has to be held, and it's that expression we just derived for the passing streams. And let's put that XF in there, just like we did the other two times. Okay, so let's let X tilde equal XF. Let's try that one. Okay, so here's the mass balance at the feed tray. So that means that if X tilde equals XF, Y tilde, the passing stream at the feed tray, has to be equal to L minus L, V minus V bar XF plus XFF over V minus V bar. All right, so that gets us only so far. We're going to look on the last the last constraint. So the last constraint is about something called the feed quality. And that's related to the issue of whether or not the feed comes in as a saturated liquid or a saturated vapor. Okay, so we're going to define quality. I need to take a quick break here, so we'll move on to part 2 in the next video.